In this presentation, I'll be explaining solar radiation geometry. Now continuing solar radiation geometry, let us see different solar radiation angles used for different analysis. The first one is called the latitude angle. Latitude angle, that is represented by phi. Second one we call it declination angle, delta. Third, hour angle, omega, or sometimes it is capital H also. Then altitude angle, alpha. Zenith angle, theta z. Surface azimuth angle, gamma. Solar azimuth angle, lambda s, gamma s. Tilt angle or slope, that's called beta. Angle of incidence, theta I. So these are the different angles used in the solar radiation geometry. We will see one by one in the next slides. Let us see first one, latitude angle, that is represented by phi, or that is the latitude of location. Location's latitude. The latitude angle phi is the angle made by the radial line which joins the given location to the center of Earth with its projection on the equatorial plane. For example, this point, to find out the latitude angle of this one, its projection is taken on the equatorial plane, at this one. Now what is the angle made by this projection with the angle made by the line joining the given location from the center of Earth, or this angle? What is this angle between this and this one? This angle we call it as, that is, position of the observer is here, and that is making with the center of Earth a straight line, and that what is the angle made by that line with its projection on the equatorial plane? That angle we call it as latitude angle phi. Or it is an angular distance north or south of the equator measured from the center of Earth. It is an angular distance also. It varies from 0 degree at equator, that is, this one will be 0 degree along the equator, and that maximum value equal to 90 degree at the poles. 0 degree at the equator and 90 degree at the poles. Latitude angle is positive for the northern hemisphere and negative for the southern hemisphere. So that's the polarity is positive in northern side and negative in the southern hemisphere. That is the latitude angle, that is latitude of location. Next angle is called the declination angle, that is represented as delta. Declination angle, delta. Declination angle delta is the angular displacement of the sun from the plane of Earth equator. From the plane of Earth equator, this is the sun and this is the plane of the equator. But this angle we call it as declination angle. Or in this one, if you see that one, see this is the sunrise as that one. Therefore, this is also sunrise parallel to that one, and this is the equator plane and semi parallel to that one. Or this can be considered as a declination angle. The angle is angular displacement of the sun from the plane of the Earth equator. That is called declination angle delta. Or it is the angle between the line extending from the center of the sun to the center of Earth, from the center of the sun to the center of Earth, and the projection of this line upon the Earth equator plane. And it is due to the tilt of Earth axis, and it varies from plus 23.5, that is in summer solstice, as in June 22 it is 23.5, and it is equal to minus 23.5 degrees in winter solstice, that is December 22nd. Declination, that will be varying with the month, for the season it will be varying. But the declination angle is positive when measured from the measured above the equatorial plane in the northern hemisphere. That is positive, other case it is negative. Therefore, declination angle will be varying as months changes, and that is 23.5 during June 22nd and minus 23.5 during the December 22nd. To calculate the declination angle delta, the corresponding equation is delta in degrees equal to 23.45 sine 360 divided by 365 into 284 plus n. That's the equation in which n is the total number of days counted from 1st of the January till the date of calculation. As an example, on April 30th, let us calculate what is the value of the delta on April 30th. In April 30th, if you calculate from the January, there are 120 days are there. Therefore, you are substituting 120 here and you are calculating delta in degrees. If you calculate that one, you will be getting it is equal to 14.56 degrees. 14.56. That is from this graphical representation, it is very clear. In April here, near to April 30th, that will be corresponding to here that comes, that is 14.56 degrees. Therefore, this is the pictorial or graphical representation of the variation of the declination angle as for different months as such. Therefore, the declination angle equal to plus 23.5, as I already explained, it is equal to in June, and in December it is equal to 22nd, and December 22nd it is equal to minus 23.45. Therefore, as months changes, the value of the delta changes as a sinusoidal fashion like this. One is inclination angle is there. That is, tilted position of the earth axis is known as inclination angle of the earth axis. The axis of rotation of earth is tilted at an angle 23.5 degrees from the vertical line, 23.5 degrees perpendicular to the plane of our planet's orbit. The tilt of earth axis is responsible for the various seasons, and the inclination of the axis along with the revolution around earth gives seasons. Therefore, that is because of this inclination angle, which is equal to 23.5 degrees. Next angle is equal to hour angle, that is represented normally omega. Some books it is written as capital H also. It's called the hour angle. Hour angle, the angle through which the earth must turn to bring the meridian of the point directly in line with the sun's rays. Or it is measured from the noon based on the local solar time LST. Positive during the afternoon and negative during before noon. Before noon it is negative and afternoon it is positive. Let us calculate that one. For hour angle is the measure of the time of the day with respect to the solar noon. With respect to solar noon, what is that one? That is the reference we are taking. This is the solar noon time is that before and after that one. And here before this one and after here. And if it is that, the corresponding equation is that omega equal to 15 into Ts divided by 60 minus 12. This equation can be used 15 into Ts by 60 minus 12, where Ts is the solar time of the day in minutes. As an example, we consider first if at noon omega equal to 0, at noon here omega equal to 0, but assume that at 10 a.m. One more thing is that the per hour change is omega equal to 15 degrees. Omega equal to 15 degree per hour, or we can say that one 4 minutes per degree. It is actually changing equal to per degree 4 minutes is there. Therefore 15 degree 1 hour is, therefore omega equal to 15 degree per hour. Now if you calculate the hour angle corresponding to 10 a.m. which corresponds to 10 hours. If you substitute in this one, 10 hours means that 10 into 60 divided by 60 minus 12. Therefore, it is equal to 10 minus 12 minus 2 into 15, or that's equal to minus 30. omega equal to minus 30 degree. Therefore, our angle corresponding to 10 a.m. that is equal to minus 30 degree. Now the same thing at 2 p.m. which is equal to 14 hours. 14 hours means you substitute here in 40, 14 into 60 divided by 60 minus 12, or that is equal to 14 minus 12, or 2 into 15 which is equal to plus 30. Therefore, here our angle corresponding to 2 p.m. or 14 hours, it is equal to 30 degree, and for 10 a.m. or 10 hours it is equal to minus 30 degree. For forenoon case, that is equal to all are negative. Here it is equal to negative, and for afternoon the omega value or the hour angle equal to positive. Next one is the altitude angle, alpha. It's represented as alpha. The angle between the projection of the sun rays. For example, here this is the sun, the center of Earth, equatorial plane. Therefore, the angle between the projection of sun rays on the horizontal plane. This is the sun ray, and its projection is this one. Its projection on the horizontal plane is this one. The angle between these two, that angle we call it as Earth's surface and the direction of the sunrise. This angle we call it as altitude angle alpha. Therefore, the angle between this line and this one, this angle we call it as altitude angle alpha. The same thing here also shown here. This is the sunrise, and here its projection on this angle, that is this angle. Of course, the sunrise here. This is not shown the alpha as such here. This on this one, what is the angle made by that one? That is the altitude angle alpha on this. Therefore, this altitude angle is the maximum at the solar noon. Therefore, as the sun moves here, that altitude angle will be maximum when it at the solar noon. Therefore, altitude angle changes as time changes, and that is the angle between the projection of sun rays on the horizontal plane on horizontal plane on Earth's surface and the direction of the sun rays. Therefore, this angle we call it as altitude angle. Next one is called zenith angle theta z. Zenith angle or theta z is complementary angle of solar altitude angle. Already we have seen what is the solar altitude angle is equal to the angle here and between the projection of that on horizontal plane. This angle is called altitude angle. So this is a vertical line perpendicular to the plane as such. Therefore, this angle, this sun ray line as well as this vertical, now this angle we call it as zenith angle, or this zenith angle plus the altitude angle equal to 90, or theta alpha plus theta z should be equal to 90, or we can say that one these are complement, that is zenith angle theta is complementary angle of the solar altitude angle, or in a way theta alpha plus theta z is equal to 90 degree. For vertical angle between sun rays and a line perpendicular to the horizontal plane through the point that we call it as the zenith angle. So this angle is called the zenith angle. Angle between the beam from the sun and the vertical. Therefore, this is the beam from the sun and this is a vertical line. That angle we call it as, this angle we call it as zenith angle theta z, and theta z plus alpha, that's equal to 90 degree. Next one, solar azimuth angle gamma s, or it is defined as the angle on a horizontal plane. This one, angle on a horizontal plane between the line due south, that is this line, between this one line due south and the projection of sun's ray on the horizontal plane. That is this one, projection of sun ray on the horizontal plane, and this angle we call it as solar azimuth angle gamma s. It is taken as positive when measured from the south towards west. It is measured from the south towards west. Now, if you measure from this one, this or this direction, it is taken as positive. The same thing pictorially represent another form. Now here, this is the angle between the line due south, that is this one, this line, and the projection of the sun's ray on the horizontal plane, this one. This angle we call it as solar azimuth angle, gamma s. Surface azimuth angle, gamma. That is the surface azimuth angle is the angle between south, that is between south and the horizontal projection of the surface normal, that is this one, this horizontal projection of this surface as such. This angle we call it as surface azimuth angle, and it taken as positive when measured from the south towards west, that is measured, that is from south towards west side, that is measured, that is in this direction, is taken as positive. Therefore the surface azimuth angle is the angle between south and the horizontal projection of the surface normal, that is, it is actually projection of the surface, that is this one, this surface is projected, and that angle we call it as gamma, surface azimuth angle, gamma. Now let us see tilt angle, or that's called slope, beta, and then we'll see what is angle of incidence. Let us see first beta. This is the plane, horizontal plane, or which this is a tilted one, inclined plane. This is an inclined plane as a, this is a horizontal plane. This is an inclined plane, that is making an angle beta with respect to the horizontal. Therefore, the angle made by the inclined plane with respect to the horizontal, that is we call it as tilt angle beta. Therefore, the tilt angle is the angle between the inclined plane surface, that is this one, that is called collector, actually solar collector, solar radiation collector, and the horizontal plane. This is the horizontal plane. This angle we call it as tilt angle, or that's also called slope. The same thing shown here. This is the tilted plane, and this is the horizontal plane. This angle we call it as the tilt angle. Now this is called the solar radiation falling on the tilted plane and perpendicular to the line, that is an angle is made by this ray with perpendicular to the plane, that we call it as, that is called the theta I, that's called angle of incidence. Therefore the angle of incidence for a surface is defined as the angle formed between the direction of the sun, that is this one, the direction of the sun ray, and the line normal to the surface, and this is the line normal to the surface, and this is the sun ray direction, and this angle we call it as angle of incidence theta I. Therefore this is the angle of incidence theta I, and this angle, that is angle made by the inclined plane with respect to the horizontal, that we call it as tilt angle. Therefore the same thing shown here, this is a ray falling on this plane, and this angle we call it as tilt angle theta I. This shows the array orientation, direction of the radiation. This is the direction of the radiation and the zenith, and this is the incident angle as such. This is the angle, the incidence, and this azimuth angle. This is the tilted solar array, and this is called the tilt angle. This is called the tilt angle, and this angle made by this one south, this is called azimuth angle. This is called the azimuth angle, and this is the west, this is the east, and this is the south and north, and this angle made by this one, this is called azimuth, surface azimuth angle, and the array orientation can be described using azimuth and tilt angle. For the orientation of the array can be defined in terms of tilt angle and azimuth angle. This is the azimuth angle and this is the tilt angle. Therefore, this is the radiation incident on the solar panel. Now let us see a tilt angle calculation. These are the steps involved in calculating the tilt angle of a solar collector or PV module. Tilt angle calculation. First step is that find the latitude phi of that point where we have to calculate the tilt angle. We have to first find out phi, and then find the n, which is the total number of days counted from the January till the date of the calculation. Knowing the n, then you can calculate what is the delta. Declination angle can be calculated, as I already explained, that using that equation you can calculate what is the value of delta. And then once you know the phi and delta, then you can calculate what is the altitude angle of the sun. Altitude angle can be calculated, that is, here look in this figure you can say that one, this is the perpendicular to this earth surface here, and angle made by that one, that is by the sun rays, that angle we call it as the alpha, that is called the altitude angle. This alpha equal to, alpha can be calculated, you can see from this, looking from this figure, the alpha equal to, that is, this is totally 90, this zenith line, no, that is altitude angle plus zenith angle equal to 90. Therefore this is alpha and this is a zenith angle, or alpha can be written as 90 minus zenith angle, or zenith angle can be written as this is equal to this angle, that is phi, minus what the delta, that is the declination angle. Phi minus delta equal to this angle. Therefore alpha 90 minus phi minus delta, that will be this one, 90 minus that one equal to alpha, or alpha equal to 90 minus phi plus delta. Therefore the altitude angle equal to 90 minus the latitude angle plus declination angle delta. That is from the figure, this is clear. Therefore as per once you calculate the alpha, the tilt angle can be calculated as, because tilt angle plus alpha equal to 90, or tilt angle, the required tilt angle equal to 90 minus alpha. Therefore the steps are there. First from phi, and then you calculate delta, and knowing phi and delta you can calculate what alpha. Knowing alpha you can calculate tilt angle equal to 90 minus alpha. These are the steps involved to calculate tilt angle, required tilt angle. As an example, find the optimum tilt angle for a south facing the photovoltaic module in a place that is to zone, that is latitude equal to 32.1 degrees at solar noon on March 1. These are given here. For the latitude equal to 32.1, that is given, and March 1. March 1 means you have to calculate what are the number of days from January 1st. That will be getting, it is equal to 60 days. Knowing n equal to 60 days, you can calculate what is delta. From this equation, you can calculate delta, that is equal to minus 8.3 degrees. For delta declination angle equal to minus 8.3 degrees, and the phi is equal to 32.1 degrees, then you can calculate what is the angle, altitude angle alpha, which is equal to 90 minus phi plus delta, or that is equal to 49.6 degrees. Therefore alpha equal to 49.6 degrees, that is altitude angle equal to 49.6 degrees, and tilt angle can be calculated, because tilt angle plus altitude angle equal to 90, or once you calculate the altitude angle, you can calculate how much is the tilt required for the solar panel, that is equal to 90 minus altitude angle. Therefore 90 minus alpha, or 90 minus 49.6 degree, which is equal to 40.4 degrees. Therefore the tilt angle required under this condition, or this location under this date, or this much you can calculate as tilt angle required is equal to 40 point, this angle equal to 40.4 degrees.